Hey everybody, today we are going to be deriving a formula for what's known as concatenation. So what it is if you're taking, let's say, I don't know, 141, and you're taking 216, okay? And you're going to do an operation, and this is going to equal 141,216. It seems pretty straightforward. You're like combining them together. It's used a lot in computer science, whenever you have to write a script that takes different components of different things and mashes them together, kind of like this. That's probably, if you've heard of concatenation before, that's probably where you've heard it. In math, it's kind of used sometimes, but not really. And there's a notation for it where you just put like two absolute value bars between the two numbers, and that's kind of your notation. So we're going to derive a formula for it because there exists some formula that makes this a true statement, okay? So our goal, so I'll write here goal, is to find to find a formula where we can get A concatenated with B to be equal to some number C, okay? And that's a formula. That's our goal. Our goal is to find a formula to be able to do that. So, I'd say first we should make some observations, alright? So I'm going to erase the goal so that we can have some space here. So we should make some observations. First, we can see that the last number is going to take up these last two digits. So let's call this our A, and let's call this our B. So our B is there, okay? And so we can actually, technically this is our A here. That's our A right there, but we can't just write A, B, that's multiplication. We're not multiplying them. We can expand this out to be, let me do it like this. So we have 141, but it's not just 141 because we're multiplying it by 1,000, so it's 141,000 plus our 216. That is our term, so I can do that. That is that term right there, okay? So that's cool, right? What's significant about this? Well, again, our B remains here, so I'm gonna actually write that down. Our B stays there, okay? But our A is now A times 1,000, which is interesting. So we have A times 1,000 plus B, and that's equal to A concatenated with B. So that's pretty interesting, Now we just have to find where that 1,000 comes from. Well, if our B was smaller, let's say if it was just 21, our number would be 14,121. So then our A would only be multiplied by 100. So we can understand that our A is the number multiplied by A is dependent on how many digits B has, okay? And we can also understand that the number that we're multiplying by A is going to be a factor of 10. So those two constraints kind of start to build some sort of connection that we have here. So we're going to have to find a formula that counts how many digits are in our B, just our B number, basically. So how can we do that? Well, there is a cool property about logarithms that allows us to be able to find the number of digits a number has. So let me write these down in blue over here. So if you take, let me write down the logs for log of, 10, log of 100, and these are all base 10 logarithms, just so you know. So, and log base 1,000. And for the sake of it, let me put log of 1. Okay, so these are some known values of our logarithms. Log of 1 is 0. Log of 10 is 1. This is 2, and this is 3. So as you can see, if we add another 0, which corresponds to multiplying our previous number by 10, or another factor of 10, each new 0 adds 1 to our result. So this has 0 zeros, so our number is 0. This has 1 0, 1, 2 zeros, 2, 3 zeros, 3. So it's like the number of zeros corresponds with our number. So you can think of log of 1 followed by 10 zeros is going to be 10, okay? Which is cool, but we can't just say, oh, it's dependent on the number of zeros. There has to be some other connection, some other more mathematical connection. So you can think of, well, okay, log of 1, this is just log of 10 to the 0. That's kind of the definition of a log. Because if we do log of 10 to the x is equal to, I don't know, 5, okay? We can raise both sides to the 10, and now we get 10 to the x, because these two things cancel out, is equal to 10 to the 5th. And then from there we can conclude that x equals 5. So it's kind of the way logs work, and so this isn't some abstract thing, it's just kind of like definitions right here. So then this is log of 10 to the first power, this is log of 10 to the second, and log of 10 to the third. And you can notice that, let me make it explicit here, this number corresponds with that number. So you can conclude, let me do the 3 dots there, log of 10 to the x is equal to x. So that's actually really useful for us, because we can use our number here and kind of plug it in, because we don't know, let me do this in black here, actually, let me put these here. We don't know the exact value of log of 216. I mean, we could figure it out if we sat here all day and tried to compute it, or we could use a calculator, but we don't know this, okay? We could approximate it, or we could actually just put it in a range of stuff. So we know that this is going to be between log of 1,000 and log of 100, okay? Because 216 is between 100 and 1,000, so we can say that this is going to be between these two numbers, which are numbers that we know. So we can put log of 216 here, and they're between, well, log of 100 we said is 2, and log of 1,000 is 3. So we know that log of 216 is between 2 and 3. And this is going to be true. If we had a 4-digit number, it's going to be between log of 1,000 and log of 10,000, which are 3 and 4 respectively. So this actually tells us a lot about what we have. And so this higher number up here has 3 digits. Or I'm sorry, it's 3, which 216 has 3 digits. Okay? So this is going to be true for all cases. You can test them if you want. So basically what we're going to do is we're going to take the higher bound, and yeah, so what does this mean? Okay, we're basically taking our number, taking the logarithm of our number, estimating the two ranges it could be between, or the range it is between, and taking the higher bound. We're like rounding up, because this is probably going to be closer to 2, so it's going to be like 2.2 or so, something like that. But we're rounding up. We're not rounding down, we're rounding up. No matter what our number, even if our number is 2.0001, we're still going to round up to 3. Now, if it is exactly 2, then we will stay at 2. So, basically, we're going to round up. Luckily, there is a function for that. it is called the ceiling function. Ceiling. And it's denoted by that. So we have like two little, like, it looks like absolute value bars, but with like a ceiling at the top. And then there's also the floor, which is the opposite, so it looks like a little floor. Okay, but we're not going to use this. This is the one we are focusing on today, because we can see here that since log of 216 is between 2 and 3, the ceiling of log of 216 is 3. We don't need to know the exact value, we just need to know its ceiling. So this is some integral part of finding our concatenation. Why does this matter? Because remember, we need to know how many digits are going to be in this number that's multiplied by a. So this is actually extremely helpful. So if we can generalize this, this is going to be the floor of log b. Okay? And that's going to tell us the factor of 10 that we're going to multiply that by this. Basically, this 3 here, this is 10 cubed. And that's exactly what we need. We need a 10 cubed. And so what we're doing here is we're taking this 216 and then devolving it. We're basically saying like, okay, 216, if we round its log up, it's going to be 3, which makes it 10 cubed, so it's 1,000. So we're kind of like rounding this up to the lowest number that has an additional number of digits. So like if this was 216, or I don't know, 2,160, we'd go for 10,000, because that tells us how many zeros we're gonna have here. So basically, if we raise this, so we have the 10 here, so if we raise that, so if you do 10 cubed, that's what we're going for. So we're basically raising this 10 to the log of b, to the ceiling of log of b. And that's actually really close, because look, that's the number we're multiplying by. So essentially, we have the formula, because all we have to do, let me just make that a little bigger, multiply that by a and add b. That's kind of what we already found here. A multiplied by this magical number plus b. A multiplied by our magical number, this is our magical number, plus b. And that is our formula. Let me circle it in blue. Let me circle it in blue, because I think it's actually really, really cool. So our formula for a, let me do a concatenated with b, is just a times 10 to the ceiling of log of b plus b. That's actually pretty cool. Yeah, so through this whole process, we were able to derive a formula. So I think it's actually really interesting how we got it through, instead of just like doing formulas and stuff, we actually used an example and could find a cool method of doing this. And when I first did it, I was like, oh, I want to find a formula for this, because when I first saw concatenation, I was like, oh, this sounds interesting. Is there a formula for it? So then I tried to derive it. I got into many obstacles. It took me a couple hours, but eventually I was able to. And so it's kind of like motivational. Like you can do stuff like this on your own, as long as you know tools that will help you on the way. Like logarithms, you can use that to help you find the number of digits in a problem. And that branches out to other problems like digit sums and all that. So this is actually pretty cool. And yeah, it doesn't really have too many applications, but I think it's still really interesting. It's like the operation that humans, like it kind of like goes well. Like you can just like mash these two numbers together, but it has this weird formula that uses ceilings and, I mean, pretty much ceilings, but then this thing here, it's weird, it's a complicated formula for a simple function. So yeah, I hope you enjoyed, and subscribe for more random stuff in the future. Thanks.